In this chapter, we're going to use the fundamental theorem of algebra. This is a method used to find zeros of a polynomial. As you see here, this theorem, the fundamental theorem of algebra, umbrellas over several other theorems, like the number of zeros that a polynomial can have, all possible zeros, and whether or not we have complex or imaginary zeros, and how that works. So first off, let's look at the fundamental theorem of algebra. One of the most important parts is in our polynomial, we need to find the highest power, in this case, n. So what is the highest power of my polynomial? The exponent that's the largest. If that number is greater than or equal to 1, then yes, we will have zeros. If it's less than 1, if you see like a fraction or like a decimal, then we will not have any zeros. But that number must be greater than or equal to 1. Now to find the number of zeros, let's also look at the highest power. And the highest power also tells us the number of zeros we're going to have. So if that number is a 3, like a cubic, we will have 3 zeros. Whether or not they're going to be real or imaginary, we'll see later. If that number is a 6, then we can expect having 6 zeros. Now the rational zero theorem, we need to take the number in front of my highest power, in this case a, and the constant, a number without any exponent, just a number like 3. Look at those two numbers, and I need to find the multiples of those two numbers, and I'm going to divide all the multiples of C over all the multiples of A. And in a minute, I'll show you an example. The last theorem is the conjugate zero theorem, which states if we have A plus BI as a zero, then we also have A minus BI as a zero. Complex zeros come in pairs. Now they're complex because we have a real number A and an imaginary number BI. And that BI must have both the positive and the negative value. Complex numbers come in pairs of plus and minus. Okay, let's take a quick look at the rational zero theorem. First, let me go through my progressions of the fundamental theorem of algebra. Let me look at my highest power, in this case 3. Is it greater or equal to 1? It is. So I do have zeros, so I'm not wasting my time by doing this. And how many zeros am I looking for? Well, my power is a 3, so I should have 3 zeros on this polynomial somewhere. Now let me look at all potential zeros. To use this, we need to look at the leading coefficient of my highest power, in this case 4, and then my constant, in this case a negative 15. I want to find my multiples of 4, so let's see, we have 1 times 4 and 2 times 2. Now also, negative 1 times negative 4 is also positive 4, and likewise negative 2 times negative 2 is also a positive 4. So we have to account for both the plus and the minus of each of these numbers. Now let's look at 15. What are my multiples of 15? Well, 1 and 15, 3 times 5, and I think that's it. And again, we have to account for the plus and the minus versions of these because I can rearrange these to get a negative 15. Plus 1 times negative 15 is negative 15. Negative 1 times plus 15 is also a negative 15. So you got to account for the plus and the minus because you can manipulate that around. Now how the rational zero theorem works is I need to take my C, my constant, all of these numbers, and divide them by all of these numbers. So let me take 1, divide it by 1, 1 divided by 2, and 1 divided by 4. So all of these need to be divided by all of those. And again, we have to account for the plus and the minus. So let me move on to the next. 3 over 1, 3 over 2, and 3 over 4. So 3 over 1, 3 over 2, 3 over 4. And let me do the same with 5 over 1, 5 over 2, 5 over 4. And last but not least, 15 over 1, 15 over 2, and 15 over 4. Again, the plus and the minus from each and all of these. Now we're almost done. We just need to simplify these fractions. So 1 over 1 is, of course, I'll just change it to 1. We can keep this as 1/2, 1/4, 3 over 1, simplify that to a 3. 3/2, 3/4, 5 over 1 is a 5. 5/2, 5/4, 15 over 1, I'll change that to a 15. And 15 halves and 15 fourths. These are all possible zeros with this polynomial here using the rational zero theorem. Now to find out what are these zeros, one way I can do is to graph this, but that's not part of this chapter. It's in the previous one. Graph this, look at our zeros, and find the x-intercepts. Okay, now I'll do one more example here. First off, using the fundamental theorem of algebra, look at my largest exponent, in this case 4. It is greater than or equal to 1. I do have zeros. I will expect to have about 4 zeros in there somewhere. Now I need to find all possible zeros. So again, I'm looking at the leading coefficient of my highest power 2, and then my constant 3. I'll find the multiples of those. So 2 is just 1 times 2. Again, the plus and the minus of each of these I can manipulate to get a positive 2. And 3 is prime, so it's just 1 and 3. Now remember, I'm going to take the constant here, my 3, all of these multiples divided by all of those multiples. So taking 1 divided by 1, and 1 divided by 2. 3 divided by 1, and 3 divided by 2. Got to account for the plus and minus of these as well. And now I just need to simplify. 1 over 1 I can simplify to 1. I'll leave this as 1/2, and 3 over 1 reduces to just a 3, and I'll leave 3/2. So all my possible zeros here, I have 1, 1/2, 3, 3/2, -1, -1/2, -3, and -3/2. Somewhere within these 8, I'm looking for 4 zeros. Now again, some of them could be imaginary. So speaking of imaginary zeros, we're going to use the conjugate zero theorem, which says our imaginary numbers, our complex numbers, will come in pairs. If I have an a plus bi, I will have an a minus bi. So if I have a 1 plus 2i, then I should expect a 1 minus 2i to also be a 0. And if I have a 1 minus 3i, then I also have a 1 plus 3i. And if I have a 4i, I have a minus 4i. So you should expect both the plus and the minus version of your imaginary numbers. And if it comes with a number here, we again know that's a complex number. So conjugate zero theorem. If you have imaginary numbers, they should always come in pairs.